Yeah, okay.
Hi everyone, and welcome to today's session. Today I'm pleased to introduce to you Jiafei Duan, who is a fellow Singaporean and who's doing really interesting work in the field of robotics, specifically in the use of synthetic data to train visual, multimodal language models to learn from this synthetic data and use it to generalize to a lot of environments. So previously he was working at ASTAR, also at NVIDIA Research, pretty cool place, right? And now he's at University of Washington and the Allen Institute. And I'm pleased to let him introduce himself as well as take us through the presentation today. So Jiafei, please.
Yeah, thanks, John. Thanks for having me. So I think as John has introduced, my name is Jiafei. I'm a third year PhD right now at the University of Washington. I work with Theatre Fox and also Ranjay Krishna. I work mainly on robot learning, foundation model for robotics, embodied AI, and so on and so forth. So today I have the honor to give this talk on the topic of towards a unified multi-modal language model for robotics. So I think many of the audience here has a lot of experience with foundation models, especially in the various domain. And we have, we have been seeing foundation model in our everyday life with stable diffusion, generative AI from Sora or from Movie Jam, which came out from Meta a few days ago. Or even we have, have ever used, Copilot to help us with code generations, or even with the latest tool, for example, Cursor AI. And even for us, some of us who are more, academically, focused, we have been using things like ControlNet for sort of doing control-based generative models, or even definitely some of you might be using SEM2 for doing some kind of segmentation tracking, and even cool projects such as Genie, which can be used to generate, simulation games in this kind of environment. And of course, we shall not forget ChatGPT, which sort of brings the initial hype to all these foundation models across different domains. But the question that sort of always ponder me, or I'm still asking right now, is where is foundation model for robotics? Okay, so I think I press too fast. Let me just skip through and go to the next slides. Yes. Yeah, so before we answer that question, there is some things that we need to understand why people have not really been talking about foundation model for robotics, or at least we are not really actively using that. It's because there's three main reasons why foundation models works really well for other domains. I think the first one is data. So if you look at data in retrospect to robotics, the largest data set that's out there comes from OpenX embodiment, which if you convert that into token, that's about 100 million tokens. And for to train a language model using Common Crawl C4, that's over 1.4 trillion tokens. And this is drawn to scale. So that is a huge number of, in terms of, the kind of data that you're going to get in robotics versus internet scale data that you're going to obtain for training language or vision models. And if you look at another thing, which is model size, these are the layout of all the different model size based on their training parameters. And the largest that we have in the field of robotics is RT2, which is up to 55 billion different parameters. And obviously for training paradigm, people in vision and language, they have really good data curation methods with different approach from prompt engineering to using synthetic data to using memory augmented architectures. So that's something that's really missing in robotics. And there is existing work that work towards building foundation models in robotics. And right now I will cover a few I'll cover a few category of that. And then we can see, moving forward from there. So the first approach where people use is, your input will be text and language. And people will tend to use off-the-shelf vision language models and incorporating that with visual prompting, in-context learning, or even chain of thought reasoning, and basically using that as an API call to call skills. These skills can be primitive skills that's already predefined, or calling generated codes that's able to generate actions, or even incorporating this with task and motion planning to solve for the downstream action. And then we will use robot skills, by all these API calls. And then the last part will be the robot control, which is the low level controlling the robot to move to the position to execute the task that it requires to do, condition on the language and the image observation. So there has been a bunch of work that focus on this, things like manipulate anything, Vox Poser from Stanford, which tries to predict 3D affordance, 3D affordance mapped using VLM, or even MoCA, which is visual prompting, and like Recap, which is one of the latest work, and even using language model to directly output plans in the form of like code, such as prop prompt or code as policy. So for this approach of working towards robotic foundation model, they're really highly generalizable across domain because they just leverage off-the-shelf VLMs straight away without actually fine-tuning it. So if you talk about VLMs, they are general purpose language models that's able to visually understands the kind of input that it takes and generalize across different domains. And that's been shown in literatures from all these foundation models work that's out there. But however, the problem about using off-the-shelf VLMs is that they are more modular and they are less robust to like low-level policies, which is really important for robotics because you want to have precision control. You want to be able to tell the end effector to move to the exact location to perform the task, or grasp the object by the exact location in order to succeed in doing that task. So interacting with the real world is much more complicated as compared to generating a text prompt or doing some kind of generative image. And the next thing that we want to look into is that a lot of this requires high level of prompt engineering, which is going to be a huge problem because you are not going to be able to get consistent performance or even like reproducible performance if you are just consistently trying to prompt it, and then you are using off-the-shelf models, so there is going to be bound to be a difference between different models, and that will actually effectively affect the downstream performance of the task itself. So that's one spectrum of how people are using foundation models in robotics. Another approach where people try to leverage these foundation models for robotics is to do pre-training. So there is work such as like RT2, Auto, OpenVLA, which they try to comb this paradigm whereby the input is text, language, or robot state, and you train an end-to-end vision language action model, and the output will be direct robot control. So these are some of the action-based models that's currently out there. And some of the points about this kind of model is that they are really robust because they are definitely action-based models, so they can react, and respond at a really pretty decent frequency, control frequency. And also they are more visually generalizable across, different objects. However, it still requires some kind of in-domain fine-tuning before it can transfer to a new skill or even to a new environment completely. So there is still bound to be some bottleneck. And what I was trying to propose about is the third way that we should actually leverage foundation model in robotics, which could be a more suitable way as of now, which is to look at this from a problem whereby the input is text, language, robot sensors, or even robot state, and it goes into a robot instructional tuned VLM, and the output can be an interface which has like embeddings, points, or boxes, or even trajectory. So these are like a special representation, and then using that special representation, we can directly control the low-level policy, and then to affect the robot control itself. So I think this is the thing that I think we are trying to propose. And in the subsequent work that I'm going to present today, I'm going to try to cover some of this work that actually focus on this area. So the first work that I'm going to present is one of our recent work, which is called AHA. It's a vision language model for detecting and reasoning over failures in robotic manipulation. So this is an example of what I call a robot-specific VLM that's specifically fine-tuned for a specific purpose in robotic manipulation. So before we get into that, let's give a bit of intuition on what is AHA all about. So we all have been using these generative models or foundation models in our everyday life right now. So if you're a researcher or you are an entrepreneur or you are trying to hack out some product, you definitely use one of these. So for example, on the left, we have a generative model called Dream Machine. And if your language prompt is to navigate the robot in between the chair, the output of that model will look something like this. So as much as it looks really realistic, this is generated video. Or for us, we can ask ChatGPT to write us a few lines of code to draw a radical plot, or have a template to draw a radical plot, and that's what you see in the center. Or even to use VLMs in a way that we can actually prompt it to generate actions, like what manipulate anything does. So in this case, is to open the drawer, and So the question I have for everyone is, what's wrong with all these examples? So clearly all these examples are wrong because they are not doing exactly what the language instruction is telling you to do. To navigate in between the chair, the robot did not reach the chair. To draw the radical plot template, the template is totally off because, it's like six variation evaluated across 5 VLMs. There's no numbers, everything is off. And lastly, the robot manipulation, it goes for the middle drawer instead of the top drawer, which is not what you want it to be. So I guess everyone experienced this when they are using VLMs or LLMs in whatever case they are using it. So the easier ways to fix this is to make correction to that prompt. So as humans, we automatically know what's wrong with it. So for the first one, we know that the motion of the robot is not smooth and it did not go past the chair. Neither did the robot, go past the chair. And this is based on human feedback. And if just based on the human feedback, we can generate the correction prompt, which is to navigate the mobile robot between the two chairs and go past it to make it, while making the motion more realistic. And the output looks something like this, which is exactly what you want. And this is, in fact, what OpenAI has been using with RLHF to have human in the loop to give feedbacks to do alignment. So same goes as drawing the plot. Clearly, this is not what you want. If you know exactly what went wrong, which is that the label for each variations by each model is missing from the plot, you are able to make correction to that code using the same LLM that generate the code, and then we will be able to get something what we are looking for. And same goes for manipulation. So if you are able to detect why something failed, we are able to give that feedback, and using that feedback or condition on that feedback, we are able to do replanning. And so in the replanning case, we'll retry and resample a different detection. And this time you'll detect the right object, and then the task will succeed. So humans learn through failure. I think that's the argument we have here. But honestly, what we believe is that humans learn through understanding failure. And that's a really powerful tool. And that's something that we want to leverage in fine-tuning this VLM for doing robotics tasks. And that's why, that's the aha moment here. Yeah, so here are some of the related work in identifying failures. So manipulate anything has a recovery mechanism, which uses VLM to identify failures. Scaling and distillating down also uses language models to actually identify failures based on the state information. Eureka is a well-known work that actually has a reflection mechanism, which reflects on the reward that you obtain based on the initial sample, and using that using that as a feedback mechanism to improve on the LLM generated dense reward function. Reflection is a really well-known work that actually tries to use a kind of a scene graph setting to actually predict what went wrong in robotics context, or another work is replant. So the idea is that people in robotics have been working on failure detection, but a lot of times they don't work on reasoning. So what I mean by failure detection means that given the formulation that you have a sequence of action, you ask whatever model you have, to determine whether these succeed, and this success will often end up being a binary success of 1 or 0, and then based on that condition, you then reiterate on that same time step by trying out something different. But that's not how humans give feedback, and that's not how humans identify failures. So we want to propose a different formulation. We want to, given the current time step, we want to be able to determine the success condition. We want to know exactly when did it fail, and we want to definitely know what is the reason that something failed. And that will really be really useful to help us, to improve on some of these downstream robotics applications that leverage heavily on foundation models. So with that, we need to be able to generate data of failures. So to be honest, it's really easy to generate failure data in the real world, especially when people are collecting data for training robotic policies. But not many people actually save that failure data. In fact, failure data are less likely to be used in any of this kind of process. So in that context, we have to find ways of alternative methods to generate failure data. So in our work, we look into simulation, because simulation is something that you can control, and you are able to generate a huge scale of this kind of data. So with that, we actually look into simulation. So in simulation, we have this simulator here, which is RL Bench. What it does is that if you look at a successful trajectory, it can be broken down into many subtasks. So for example, closing the rate jar, you can break it down into multiple subtasks, And between each subtask are 2 consecutive waypoints with language annotations that comes with it. So now we have the good demonstration. So the idea here is how can we take the good demonstration and make it fail? So we define a list of failure taxonomy. And these failure taxonomy are not defined just purely by us. We did a bunch of surveys to look at existing policies and why most of these policies tends to fail. And then we are able to procedurally generate in simulation this failure condition by just altering the successful trajectory. So for example, an incomplete grasp, we basically retain that grasp to be open as it's supposed to grasp the object at that point. So by doing this kind of perturbation, you are able to actually generate a bunch of these failure examples. And you know exactly why it failed because you are the one that sort of generated. And with that, we propose the AHA fine-tuning data set. It contains about 79 different diverse tasks of failures of like a total of 7 different failure modes and up to about 49K different image text pair of failure reasoning. And then this is how it looks like. We basically concatenate the frames to sort of incorporate the temporal relation. And also we provide n number of multi-views, so for the models to take in. And then obviously, once we curate that data, we want to be able to do instructional tuning on that data. So we did instructional tuning on Llama 2 with the same kind of training process as Lava. And we also incorporated co-training to incorporate more general knowledge into the fine-tuning process. And then for us, we fine-tune we fine-tune only the LLM and also the projection layer while freezing the image encoder and the tokenizer. Yeah, and of course, it makes no sense if I'm just evaluating on our own domain. So VLM is supposed to be general purpose. So with that, we propose a total of 3 different evaluation data sets to test whether is our model generalizable across embodiment, across domain, across simulation. So for the first one, we have the RL bench simulator, but in this time round, we have 10 held out tasks. So this task was never seen during the fine-tuning phase. And next, we have reflection, which is a third-party data set of failure that was curated by one of the team from Stanford. And then it contains videos of robot failing. And this embodiment is totally not seen during training. And last one, we actually implement the failure bench into a different simulator, which is called ManyScale. And then we generate a bunch of these failure examples in ManyScale. And we use that as our evaluation data set to actually evaluate AHA's capability in reasoning about failure. So with that, here are some of the empirical results on evaluating on these 3 data sets. We show that, AHA actually outperforms both open source and closed source VLM significantly across all 3 of these data sets. And also we shows that, AHA actually obeys a scaling law. And basically what you try to say is that the more data you generate, the better, the performance of reasoning AHA can be. And also to make it fair, because this is open vocabulary reasoning, so we actually evaluated across 4 different evaluation metrics to be much more vigorous. We have the traditional ones which people in NLP will be using, such as cosine similarity, and even for like robotics, we focus on binary success, and more modern approach of evaluation, such as using LLM fuzzy match. And we use a third-party model, which is from Anthropic. And lastly, there's no point to fine-tune a VLM if it doesn't retain any of its general world knowledge. So we actually evaluated that, and we evaluate our VLM with the the inspired VLM, which is Lava 13 billion, and then we evaluated across 5 different common VQA benchmark, and it shows that our model actually retains the general knowledge that it's supposed to come with. And here are just more examples to show that AHA's capability in terms of reasoning across different embodiment, different tasks, and also different environment. So as you can see here, there's the prediction of AHA versus the ground truth answer. And on the right side are videos showing that we evaluate AHA on different video sequence of robots that is not from the same training data, camera views that's totally different, environment that's different, visual domain that's totally different. And we show that, AHA really works really well in terms of providing decent reasoning to explain why something failed. So the question is, having a VLM that's really good at explaining why something failed and detecting failure has no meaning if you can't use it for any downstream tasks. So that's where we look at it from the second part of the paper, which we proposed 3 downstream tasks. And we are not limiting to 3 downstream tasks, but we are just suggesting 3 downstream tasks that this failure reasoning can be used for. So the first one is we use it for VLM-based reward function generation. That means you use approach that can generate dense reward function for RL training, work such as Eureka, and then we incorporate AHA into it to actually feedback about why something failed. And once you know that something fails, you are able to regenerate a better reward function in a faster iteration phase. And the second one we look into, which is like using VLM for task and motion planning. So the traditional ways of doing TAM is that we have a planner that's able to generate plans given the different constraints, given the different kind of objects and primitive actions. But nowadays, there's more TAM systems that leverage on LLMs to generate the task plan in order to execute the task. And however, most of the time it might fail because it doesn't align to human intent. So we have AHA to be in the loop to actually provide reasoning on why it fails and use that reasoning to re-edit the generated plan. And the last one we look into, can we use AHA to actually do sub-task verification? That means, can we detect whether a sub-goal has been achieved? If it does, give a 1. If it doesn't, give a 0. And then using that to actually improve the performance of this kind of downstream policies. So we evaluated that on a bunch of tasks for different applications. So I'm going to show you guys on VLM for reward generation. So this is the 5 tasks that we have evaluated on in many scale simulation for RL reward generation. So you have a LLM that generates a dense reward function, for example, for the task of stacking a cube. And then you train the policy, in this case, you train PPO, and it doesn't work, obviously, in the first iteration. But once you have the rollout, you ask AHA to feedback on the rollout. And using that feedback, we regenerate the code. Now you actually incorporate a new line of code which says penalty for the misaligned in the Z direction. And that actually helps the policy to accelerate its learning. And the next iteration is able to train a policy that actually does what the original task is supposed to do. So if in the traditional Eureka setting, it basically becomes a search problem, whereby you're generating many different reward functions and search through multiple iterations. But now with our approach, you are able to do it within as quick as 1 iteration with 1 sample. Obviously, we can also use the failure detection for task and motion planning. So in this context, we actually try on this task and motion planning setting, whereby we have like a bunch of goals. So in this case, we want to move the banana to the span camp, and we incorporate a process, which is a paper that came out recently. They use language model to generate the task plan, and obviously in this context, the task plan failed. So we actually use our reflection to be able to improve on the generated task plan, and now the outcome of the motion plan actually succeed in doing the task. And lastly is our previous work, Manipulate Anything, which is a zero-shot VLM data generator. So in this context, it fails to pick up, it fails to close. So in this context, it fails to close the gripper, and then with AHA, we are able to detect that and feedback the information into the system that runs this whole zero-shot generation. And then now we are able to make correction, having a correction mechanism in place to actually solve that task. So these are just a few examples that I show that how failure feedback can be used, incorporating into the whole pipeline that leverage on foundation model for robotics, and how this VLM can be really useful to actually help to improve performance and to do some kind of real world recovery. So with that, I'll move on to the next word that I would like to present, which also focus on a specialized VLM. And as you can see from the previous work, we leverage on simulation. And this work, we also focus heavily on simulation because, to do instructional tuning on some of these VLMs, it's harder to actually get real world data, especially for robotics. Because as you can see from the previous slides, I show that the largest robotics data set only add up to 1 million token. And that is really small as compared to other kind of data set from internet scale. So for this work, we focus on, which is called RoboPoint. is led by Wen Tao. So this work focuses on vision language model for spatial affordance prediction for robotics. Obviously, this is a more general purpose VLM, which you can also use for general purpose pointing or like reasoning that you want to do with it. So I think what we're trying to bring across is that, action representation really matters. So the ungrounded actions are, weakly tied with its observation, and it's really poorly generalizable. And, things that is really generalizable and strongly tied with the observation, which what I mentioned, is those that actually predicts affordance. And this affordance can be grounded onto the current scene. And you can sort of learn the action through low-level policy. And that's what we show in this work. So let me drink some water. Yeah. So in this work, we propose RoboPoint, which is a vision language model for spatial affordance prediction in robotics. Pointing is a really intuitive mechanism which humans use to communicate plans. So if you tell someone you want to do something, if language is ambiguous, you can just point. And pointing to the location give people a rough idea that, okay, I'm looking to do this thing, or I'm looking to pick up this object. And this is especially important in robotics, to provide that precise guidance. And that's why we introduced RoboPoint as a vision language model that is instructional tuned for pointing. So here's a demo of what RoboPoint looks like. So if you ask RoboPoint to place the orange onto the bottom step, you will be able to actually generate a sequence of coordinates on the image space. And then we have a low-level policy that's able to actually move the object that is supposed to be placed onto that location. And these are all done zero shot. So there was never such an image in the fine-tuning or the training process. This is a zero shot roll down. And then and one thing that I want to point out is that there is no object reference when you ask RoboPoint to place it on the bottom step. Because a lot of the work that focus on spatial reasoning, they always tends to ground to a specific object. So maybe to the left of the green pepper in this case. But in this case, we are actually free space. So free space affordance is actually much more difficult because there's no reference in that context. Yeah, of course, you are referencing to the bottom of the stack, right? So like, where is the bottom of the stack? It's kind of subjective, but somehow it's managed to be able to make the right prediction. And how RoboPoint works is it works in a similar way as AHA. So basically, we do data generation in simulation. We generate many procedure-generated scenes, 3D scenes in simulation. And then we actually have this kind of RGB with visual prompts. So we put in object assets, and we know exactly where this object asset is in relative to each other, because these are all simulation. And then we are able to do object reference. So you know that the object of A is next to the object of B, or is on the left of object B, or on the right, or on behind. So we have a predefined preposition list of the spatial relation between these objects. And then we detect where the object is, and we draw points on that object. And after that is done, we will remove the object from the 3D scene. And then now we will have the annotated points of where the spatial relation of the object is relative to something else. And all this is done in an automated way. So it's a procedure generation method. And then with that data, we are able to actually do instructional tuning on Vacuna 1.5 for 13 billion in the same kind of protocol that we use for AHA. And the output of this model is all the different coordinates on the image space. And then the input of it will be language instruction. And with that information, we are able to, in this case, we are using a graph network to actually predict a graph point or a placement point. But I guess you can use the point to guide any low-level robotic policy to do whatever task you desire. And of course, the co-training with synthetic and real-world data makes a huge component of this. So we actually fine-tune RoboPoint with both the data that we generate in simulation and also with real-world VQA data sets that sort of incorporates general knowledge into the VLM itself during the fine-tuning process. And this is just some of the empirical results of RoboPoint. As you can see, we outperform GPT, even GPT with in-context learning, and also some of the spatial VLMs. Space Lava is basically Google spatial VLM, and also Tianwen VL, and a bunch of the other models. And at the same time, we retain general knowledge as shown with AHA for reasoning. And the application for this is really tremendous. There's a lot of application, right? So right now we can't show every application, but we show 3 more prominent applications that you could use RoboPoint for. So in manipulation, I think we have demonstrated just now. It allows you to do free space reasoning and affordance prediction. So in this case, is to put on the left part of inside the pizza box. So this is really hard. This is unconstrained packing, which is a problem that's really hard to do because there's no reference of any object. Because the left inside of the pizza box, there's no reference to any other objects. So we are able to generate points, and we are able to use the low-level policy to actually place the object exactly where the user wants it to do. And we can also use it for AR, and that's pretty amazing because none of the training data contains driving or like autonomous driving. At least that was used by us for fine-tuning. So in this context, we obviously for this context require some kind of chain of thought prompting process. So we first asked the RoboPoint whether, how do we get to the carpool lane? Because it's a general purpose VLM, it will be able to tell you that the carpool lane is most likely to be on the left side of the, of the car. And then using RoboPoint again, we are able to actually navigate towards the left. And as you can see that this is consistent within frames. So RoboPoint can actually be prompted as individual frames. But if you sort of concatenate all the frames together into a video, there is still going to be some kind of consistency in the prediction as the agent moves or the camera view moves. Or another one we can use it for is for navigation. So in this case, to navigate to the empty space in front of the chair on the left, RoboPoint is able to do that. And I think one of the really cool things that I want to point out is that it's view consistent. So it's invariant prediction for view dependent relation. So in this case, maybe I'll play the video again. The problem is to locate the right side of the car. So as the camera view moves, the right side also starts to change. But somehow it still is able to predict consistently where is the right side of this car. And same goes for this, which is to predict in between the object, is able to rotate as the camera moves. So that is the work that we have done for RoboPoint. And that's, I think, one of the first work that actually look into doing instructional tuning of a VLM that's capable of pointing. And this could be used as a general purpose VLM or for specific applications in robotics. And the last work that I would like to present also is an instructional tuning VLM, which that's the whole theme of today's talk. And I think this one is a bit different. This one looks into a modality that is unlike all the other modalities that's out there. So in this work, Octopi, which is object property reasoning with large tactile language model, was led by Samson from NUS with Harold. And this work, we focus on doing instructional tuning of a large tactile language model. And that's a bit different because I would say that no VLMs or LLMs is able to actually take in tactile image. So tactile image has been used in robotics very commonly. I guess like touch is a very important sensor input, especially for robotics. Because if you want to pick up food, or if you want to detect whether is the food ready or is it right, is the avocado right, you have to be able to have a sense of touch. So that's something that is really missing, and that's the hidden mortality that people tend to neglect. And I think incorporating that with foundation models is really important. So with that, that's why we work on this work. So if you look at the traditional way of doing this, you have a task, you collect a bunch of this tactile image, you label it, and then you train a model to predict a classification model to predict whether is this tactile image right. And then you train multiple, this kind of object classification models. And every model requires a specific data for it. So that's really hard to generalize, to a large scale of different objects. So with that idea, we actually look into, can we use a language model or sort of like fine-tune a language model to be able to take in this tactile image and then be able to, output given whatever prompt you're asking. So in this case, you are grasping an avocado, is it right? So in this case, the language model should be able to reason about the object property and to give the right answer accordingly. And in this case, there's another example which shows that, once you grasp the object, can you be able to identify the object based on the tactile image itself? And also we are able to enable like grounding, which helps to, with a lot of the low level tasks, because you're able to ground it exactly on the objects that is manipulating. So for this case, to fine tune such model, we actually propose two things. We propose a model which is Octopi. Octopi comes in 13 billion and 7 billion, and also Physical, which is a data set that was curated. So to curate this data set, basically what we do is that we first, have to collect a bunch of household objects. So we collected about 74 everyday household objects, and we generated about 40 different tactile videos with 2,700 annotations. And these annotations covers object properties such as hardness, bumpiness, and how soft it is. And then updated right now, we have even more data right now for this physical. And this is how the data collection really looks like. So this is the gel side sensor that's able to measure tactile that the person is holding right now. And then once if you put the object on top of it, it's able to actually capture the tactile image, which is what you see on the right. And with that, we are able to provide the annotation of all these physical properties. And then obviously we have a process where we do inter-annotator agreement to sort of generate different language reasoning prompts that will be used for the instructional tuning. And then for this case, we actually focus on 5 different scenarios for both training and evaluation. The last scenario is a held out scenario. So we try to see whether can the fine-tuned language model be able to reason about object property description? Can it compare the different properties in terms of is this object heavier? Is this object harder than the other object? Can we be able to do object superlative selections? Can we do object property matching? And then we have a held out scenario, which is property reasoning about like doing task. And that was something that's held out. So I will cover a few. So for object property description, so if the prompt is to describe the property of this object, Octopi will be able to tell you that this object, is soft and you have a rough surface with small bumps. And then the way we do that is that we actually fine-tune Vicuna 1.5 in the same manner as what the other 2 model does. But the only thing is that we also have to fine-tune the visual encoder, because in this context, the visual encoder has never seen tactile image. So it doesn't really work. Whilst in the other 2 scenarios, you are fine-tuning with data that actually looks photorealistic as the previous data that the encoder was trained upon. And then basically you are able to also do like object parts classification. So in this case, you can see there's 2 different parts. This is a toothbrush. So one part is I think the video plays too fast. So, let me go back. Yeah, so
are both toothbrush or just, yeah.
So both are toothbrush, but they are different parts of the toothbrush. So the one on the left, I'm not sure if you guys can see it. Let me go here again. So the left one is the tip, and the one on the right is the bottom part of the toothbrush, is the harder part. So they have different physical property. And that's really important, especially for robotics tasks, because you want to grasp by the part that is the harder, right? Rather than grasp by the part that is softer. And these are also knowledge that you are not able to capture with just general purpose reasoning VLMs. So in this case, we ask it to describe, and that's the lead author here, which is Sam. And then you will be able to tell you the properties and, in terms of its material object properties and its overall presentation. And then, we can further prompt the instructional tune large tactile language model, which likely to be the handler, and that will be able to, output the right reason for us. And from experiments, we show that, with our approach, it actually works much better for some of these downstream tasks. And then ultimately, what we want to show is that for tasks such as picking up the avocado that's ready, it's hard to do it with vision alone. You need to have other modalities. So in this case, it's able to, feel both of the avocado and choose the most right avocado. And that decision-making is done by the language model itself. So what I'm trying to bring across through these 3 work is that it's really important for us to look at it, in a way whereby as of now for robotics, we should actually try to disentangle the low-level policy that's doing the task versus the high level, which is like basically having all these VLMs and LLMs to make decisions and output some kind of intermediate representations, for guiding the low-level policy. So with that, I think I've come to the end of my presentation. And hopefully, if there's any question, feel free to ask, and I hope to address any question that anyone might have. Thanks, John.
Yeah, thanks so much, Jiafei. I actually learned a lot from today's presentation. It looks like you are involved not just in LLMs, you're also involved in vision and touch. So touch came as a surprise to me. Like I think this is something that gels very well with the idea that I have, like, in order to have intelligence that can go across different tasks, you need to have the right input representations. By our body, we have vision, smell, taste, touch, those kind of senses. And I think like ChatGPT has mainly done the text modality. This robotics work that you're doing seems to be covering the rest, and eventually all this can be integrated into one big system. So
yeah,
I'm quite excited about this. And actually, I want to summarize the 3 takeaways I have, and then like maybe I'll ask one question and I'll open up to the floor. So the 3 takeaways I have for today is like this. Number 1, more modalities and better representations help to improve the capability of the robotic system. So yeah, you agree with that, right? More modalities, better representation. Second, your first paper on AHA, failing is important. So a lot of people neglected the failing portions of the data set. That's why they don't really do that well for like out of domain generalization. But if you train on the failures, it seems that you actually learn a lot more, right? That's what I took away from that. And lastly, pointing to something, which is the RoboPoint, without any kind of spatial reference, because you don't want to be limited by objects, right? This can help improve generalizability. So at least these are my 3 takeaways. Do you have any other key takeaways you want people to know after like your talk?
Yeah, so I think like I think John sort of summarized most of the things that I mentioned in the talk. I think one thing that's really important that puts robotics different from other foundation model is that we are in a space whereby data is like one of the bottleneck. To actually collect robot data is really tough, and it's not as scalable as vision and language data. So we need to look for alternatives or ways to be able to generate data either in simulation or clever ways to extract representation of real world data or like real world pre-trained policies. And I think the rationale here is that maybe we are not really at the point to do end-to-end training for all this foundation model in robotics right now, but maybe having this kind of intermediate representation, we are able to at least get like that 80% success rate that we are looking for. And hopefully with that success, we are able to generate more data and then eventually reach what we always want, to have a single end-to-end vision language action model that's able to, control any kind of robots across embodiments to do any kind of task. I think that's like the holy grail of what foundation model in robotics sort of looks like, but that's also like my personal take on this. Yeah.
I mean, on this point, okay, actually I have a few questions that I want to ask like on the different papers. But sure. I just want to ask a very, very general question because you talk about the future vision. Do you think just having the foundational model, like for example, a VLM or like a multimodal language model, like you can include touch and other sensors as well. Do you think just having that one VLM or multimodal language model is enough to generalize, or do you think we need extra structures to augment it, like memory structures, planning structures, and so on? Or can everything be done as a multimodal language model?
I think that's a good question, right? So I think we definitely have seen like really, like I guess like amazing work from OpenAI with GPT-4, GPT-4o, and towards like I guess I wouldn't say it's like AGI, but really to a really high level of intelligence. And I say that one of the huge contribution of that is data, having a lot of data for training. But I also believe that other techniques beyond data also matters. Like for example, like retrieval-based methods, or even clever ways to do augmentation to this data. How do you have like RHF in the loop to be able to refine the alignment I think that's also like other aspects that's really important that I think that matters beyond just, throwing data at the model and hopefully it will work. Yeah. So I think like both things are important, but I feel that, right now, at least for the problem in robotics is that data is one of the main bottleneck. And then we should look into how can we, leverage other ways to obtain this data. Yeah. But I guess like in the long run, like for like really, a big VLM, I think there will be a point whereby the data has so much that, like everything is considered in domain rather than everything will be considered in distribution. Right now, it seems like whatever ChatGPT was trained on is in distribution, and then that in distribution seems like it knows everything, correct? But obviously, there's going to be out of distribution scenarios. So in that case, we still need to use some kind of like techniques, as I say, right, like retrieval techniques or even like augmentation techniques or better curation techniques. But I guess like one day when there's so many data whereby the data sort of like hits a new high, then maybe everything that's previously out of domain becomes in domain. Out of distribution becomes in distribution, and then that model will be able to generalize much better. Yeah.
Yeah, this is a very nice point to make. Like the wonders of ChatGPT that people think that it's intelligent and so on. It may just be due to the massive training data, and because it regurgitates some output that you think is good, so you think it can think for itself, but actually it might just be a matter of data matching, which I think it really is. So in the case of this robot models, it's even harder to get training data because real world experience is something that's costly to acquire, and that's why your team has used synthetic data to try to bridge this gap, right, between real to sim. I believe that's the main reason why.
Yes. Yeah, correct. So right now we have been using a lot of simulation data to be able to find like, interesting representation in simulation that could be used to fine tune, this kind of high level VLMs that's meant for robotics. And then for the low level policy to be able to take in these representations and then to do the task that you want, you sort of desire to do. So that's what we are doing right now.
Correct. Actually, I want to continue this conversation, but I think I will take up all the rest of the time if I continue this.
Yeah.
So let's talk about the future, because I do have some ideas about how to learn beyond just the foundation model, like what structures to learn. We can talk about that later. Let me just ask my quick question on the first paper, then I'll open the floor for the rest. So if you go down a few slides on the RLHR, this one, yes, this slide, one slide. So I just wanted to ask, like, you mentioned that, RLHF helped to make the prompt a bit more precise, so that the robot can go between the chairs for the dream machine. By the way, it's really cool. Like I thought that was a real video that's generated. So I'm just curious. Can just prompting it better without even the RLHF step like already work to get desired behavior?
Yeah. So I guess like definitely you can do prompting it better, right? Like you can improve the prompt. You can give more in context learning. You could do like chain of thoughts and whatever other prompt engineering methods that's out there, to sort of improve it. But if you're talking about, doing this at an automated level, then you can't be always doing prompt engineering because it's going to be really labor intensive for humans to sort of do that, right? Or even to have the right kind of prompt. And then by just, doing prompt engineering, you are not be able to get robust, consistent output. So I think the rationale that we have here is that, the initial prompt definitely doesn't express what the user wants, what is the desired outcome, the desired intent that the person have in mind. But with our system of AHA, we're able to identify what went wrong, and then using that process of finding what went wrong, we are able to reiterate or refine the original prompt. Yeah, in some sense. So we are doing some prompt engineering by an automated way, and we do it in a way that the vision language model is able to detect that failure and then feedback that failure into the new iteration for generation. Yeah.
It's a reflection loop, right? Like you reflect what went wrong, and then you correct the mistake by generating an instruction.
Yeah, exactly. It's a reflection loop. I think this reasoning process is really important. I think like with like GPT 4.01, the strawberry, you have seen like reasoning actually makes a huge difference to the performance of the model. So be able to actually incorporate that reasoning from the robotics point of view, into this into a form of a VLM, definitely will help with a lot more work that come out from that uses all these VLMs, LMs off the shelf for robotics application, because they are not perfect, they are not fine-tuned, or they are not trained for specific for robotics. So definitely they are bound to make mistakes. That's why for us, we provide these VLMs so that it can help to make those off-the-shelf VM slightly better for some of these downstream tasks.
Very nice. By the way, here's a thought. So like humans, we tend to make actions and we think that we reason through our actions. Actually, scientists have found out that if you just like split brain patients where one eye doesn't link to the logical center, one eye links, they ask them to stand up with one card, and then they stand up and they realize that, hey, the experimenter asked them, hey, why are you standing up? Then they just give some excuse like, oh, I need to stretch my legs. But actually, the experimenter made them stand up by giving them the card, just that it's not fed to the logical center of the or the center that actually processes the intent. So what this actually tells me is that humans, the action may not actually be like fully reasoned out, but we do back reason quite a lot. Like after we do an action, we see what happened, and then like we try to form deductions or inferences like, hey, okay, I went to the fridge because I'm hungry. They suddenly think through, and I think this actually helps a lot with action making, decision making, because maybe the next time you want to take a similar action, you can just go through your reflection list and see what makes sense.
Yeah, exactly. I think that's like how humans learn also, in a way that from like a developmental psychology point of view, right? Like as a child, if you make a mistake, if let's say you don't really know why you make a mistake, you are more likely to make that same mistake again, because you are just retrying random things to sort of see that, okay, I'm not doing this wrongly, or am I doing this right? And then you have some kind of sparse reward given by parents, correct? Yeah. But if let's say I tell you exactly what went wrong, then more likely you will be able to do it correctly the second time, as compared to having this kind of like unguided feedback.
This is actually my entire 5 years of PhD has been to try to find a different way to do reinforcement learning without the scalar reward, because just like a parent like scold a child or like give a child cookie but never tell what's wrong or what's right, it's very hard for the child to learn actually, like because like for example, reinforcement learning, you're just either giving that cookie or spanking the robot, but you don't really tell, hey, you are failing because you are going too near the cliff and you fell off. That reasoning thing is not given. So I think your work tries to bridge that gap by having a sort of a reflection layer after failure, like why has it failed, and try to sort of like come out with a better action. I really like this process of learning from failure and reasoning through failure. This I think is something that reinforcement learning is lacking. Like that's why like there's also another part that I'm thinking of is called goal-directed learning. It's like we actually learn to do things that hit certain goals. Like we are not like saying, hey, you need to get a reward of 5. Like give you an Atari game, get a reward of 100. No one does that. Like you can't really. But what you can do is like, oh, you are in this game, like maybe you are playing Pong or something. Your aim is to not let the ball get scored inside your area. So that you can do because that's an actionable goal. But no one will be able to like, hey, get a score of 23-0. It's a bit hard to like right now for reinforcement learning, we are all focusing on the score. So that's my intuition of why RL is so hard to scale. And I mean, you're in the robotics field. Any thoughts on that? Like reward versus like goal-based learning or like reflection-based learning?
I think that's like I think that's really important, right? Because like a lot of these settings, I mean, I'm not an expert in RL for robotics, but I think a lot of these settings they focus on like
I mean, use PPO, right? It's proximal policy optimization.
yeah. So in this case,
RL.
we're using PPO, but I mean, like I personally I do a lot of imitation learning, behavior cloning stuff. So I think for my understanding of like this RL setup is that a lot of times the most optimum policy comes with like this kind of dense reward, which is really hard to write. But humans have an intuition on what might work and what might not work, in that sense, right? And I think something about VLMs or LLMs, they are really good at providing a very general kind of template for this kind of dense reward based on the high level tasks, but it's not very well grounded on like what actually went wrong. And then there won't be a ways for this, LLM generated dense reward function to sort of further improve unless you're able to, provide feedback. But just by providing feedback on the number, like how much reward you obtain from this, reward function doesn't tell you anything, correct? So what tells you is like you have actual feedback, like, okay, this robot is moving too low, then maybe the LLM will be able to take that information and generate another dense reward function that incurs a higher penalty for going too low. And then that will help to actually improve the overall training. And then, that leads to like a better success for the task, which is very intuitive as a human. Like you look at it, it's like, oh, you are doing this wrong, you are going too low. Then as someone that's, operating this, I'll be like, okay, maybe I should raise up, or like I should, turn towards the left more, turn to the right more based on this feedback. I think that's something that is really useful. And that's something we see with AHA, being able to incorporate in this kind of reward generation process.
Yeah, so I think you're in agreement with me that reward is like probably the last few layers, but the top few layers needs to be a bit more like you need to be more reasoning or reflection based.
Yeah.
Yeah. So I will leave it as here right now because I could ask for the rest of the session. So for the rest, you all have seen the 3 papers that Jiafei has presented, or you want to ask him any general thoughts on robotics or like the future of robots, please. Now's the time. You all can start asking. Yeah.
I got one question.
Oh, yeah. Hi.
Hi, Jiafei, is that how you pronounce your name?
Yeah.
Okay. Yeah, I was wondering, how would you, like, speaking of teaching a robot a particular skill, what if the skill you needed to know, like, or for it to like for a particular requirement, what if the requirement changes and it needs to unlearn the skill that it mastered to learn a new, for the new task or the new requirement?
So you are saying like, sorry,
I'll give you an example. Let's say you train a robot to drive in the USA. This is just like a hypothetical, right? So you drive on the right side here, and then you need now the robot to learn how to drive in the UK, where you drive on the left side, right? You trained it well on the right side, and it's for that at this point in time, this like you're getting better and better and mastering, and then you become an expert driver on the right side. But now, the requirement changed and I need you to drive on the left. Are they going to be able to develop robots where you can it can unlearn the skill that at one point in time, this is good. And I train my reward model to reward you well for this skill. And the longer you do it, you become really good to the point where now it's like intuitive or instinctual. But now I need you to unlearn that.
I understand your question.
So it's not as if you were making mistakes before. You were doing everything correct. Yeah.
I understand your question. So I think coming back to that, I think one way to answer your question is that if it comes with this diagram that I have here, which was inspired and took it from my advisor Dieter Fox. So I think if you look at this on the most right, which is the end-to-end model, if let's say for your scenario where you're say driving on the left, do you need to unlearn and relearn that skill? If let's say you already learn, how to drive in many different countries, then you don't really need to unlearn and relearn, right? Because that falls under your training distribution. Am I right? But that is hard.
Yeah, that wasn't like the best example. I couldn't think of one quick enough, but yeah, imagine a scenario though where you just have to change what the requirement has changed.
I see, yeah. So I think to answer that is like a general purpose robot should be able to, adapt to that easily. And the reason it adapts to that easily doesn't mean that it actually, truly transfers its learning process. It might just mean that it actually seen data that composed of, driving on the left and driving on the right. Or you have some kind of somewhere in the pre-training data, it contains such knowledge. And that will sort of like distill down into the action. So that could be one way. But the problem about that is that you require to have like a lot of this data. So in another way that if you are not able to obtain this data, how can you do the unlearning and relearning component? I think you need to leverage on capabilities on like all these like general purpose multimodal language models, because they are sort of pre-trained with like general world knowledge, right? So they know that on UK you should drive on the left, and on US you drive on the left, and
right other way around.
Yeah, on the other way around. Yeah, correct. So I think by leveraging on that to make the high level decision, but the idea of driving still stay the same, right? So in this context, driving is like a low level policy. You learn how to drive. It's just that you need to adapt to driving to the left and right. But how to drive is always like is sort of taught to you as a skill that's sort of engraved in you. So in the same concept here, right? So in this case, we already pre-train a low-level policy that's good at doing driving. So your high-level VLM will be able to decide whether should you drive on the left or should you drive on the right. So I think that will sort of help you to save the relearn and unlearn process. But eventually what we want at the end of the day is to have an end-to-end model that's able to generalize, directly across. And that will be, in the future where we have enough data of both driving on the left and driving on the right. So hopefully that sort of answers the question. Yeah.
Yeah, it does. Like I was thinking in terms of like when you make the human comparison, where you teach someone a particular skill or something, and they become so good at it, they don't have to think about it anymore. Right? It's no longer like it becomes a system 1 or something rather than a system 2. So now you're going off of instinct and you don't think. But when you develop something and you become so instinctual, like me and John talked about this before, when I use sports, like you get so good at it to do it in one way, but for a different sport, being good at it for this sport, actually it hurts you in the other sport. So that transfers to like a skill, right? Where, hey, you like for this, at some point to become a master, you need to be specific and no longer a generalist. So the more you specify, the better you are at it. But that moves you farther away from the end-to-end, model ability, which is like when you're a generalist, you can adapt more rapidly, but you're not an expert. But if you become an expert, now it becomes more difficult to make you an expert at something else.
Exactly. So I think I agree with you. That's why I say that the one that we try to preach is that, to generate a general representation, and this general representation helps you to do adaptation. So for example, imagine you learn the skill of driving. Basically, you've always been driving in US, which is on the left, and then now you go to UK, your high level sort of tell you that, okay, I need to drive on the right. And you provide that guidance, okay, now I'm driving on the right. So, but your skill, you don't really lose completely. You are still sort of doing some kind of adaptation in terms of, to this new scenario where you are driving on the right, but the skill is still retained. So obviously there's going to be minor changes, but I think these minor changes can be further refined as you start to drive on the right, and you sort of experience more of driving on the right, and that sort of append to your experience, and then the experience is basically like new data that's collected, and then you probably have enough data to do a end-to-end kind of training and develop more of a generalization capability between left and right. I guess it's a process of like being a specialist, doing adaptation, and then become more generalizable, and then continuously learning new things, and then continuously growing. I think that's like the process here. Yeah.
And would you want it to like forget, would you put in, some like ability to forget the old skill to make it more efficient, or would you just add on? I think we haven't done it yet, so I don't know.
Yeah, I think that's a good question. So I think that's a question that we never really talk a lot about robotics, right? So we always think about like, let's try to have as many skill, as many task capability as possible for a single policy. That's why there's a lot of work that focus on multitask training. So I think the rationale is that maybe it's something that we should look at it, at least in the field of robotics, which is like, can some tasks actually hurt other task capabilities? For example, like maybe learning how to do task A might hurt your capability of learning to do task B if you are doing multitask training. Or let's say learning to do task A can actually help to, improve performance while trying to learn task B. So that's something that we not really talk about. And I think that's something that we should actually look into as a field in robotics. As of now, not many work that focus on that. But I think that's a very important thing because as you say, right, when you have generalist robot, you need to be able to have a robot that can do not just 1-2 tasks, but many tasks, correct? Yeah.
Yeah.
I really like
you should lead the way in starting that.
Yeah, I just want to chime in one part here. So I really like the pipeline that Jiafei has described, where you have a language model to sort of map the input state to a certain policy, and this policy then executes out, like policies are like skills, like driving, eating, and so on. Like, so this I think is quite good because it helps to adapt different environment scenarios to like a certain learn skill. Like you want to write with your right hand, you can also write with your left hand, if you just map the inputs differently. The question I have though, oh sorry, Jiafei, can you go back to that diagram?
Oh.
So the question I have though is that my experience with fine-tuning a large language model is that it takes a long time for it to even like affect the outcome. Like you might need to train it many epochs, or like you need to run through the data sets many times to learn something new. And I think this is a challenge with adaptation to real life data. If we just use an LLM or VLM or multimodal language model, like you are sort of stuck in the training data. So if something happens, I think that's the point that was made also. Like if something happens that is different from the training data, it actually takes quite a long time to train on the new data, such that the model's outputs will be changed. Like, at least this is my experience with training language models. So perhaps, like what people are doing right now is some form of memory retrieval, like retrieval augmented generation, where you take in like experiences in memory and just put them in context in your prompt, so that you can like sort of immediately influence the output. This could happen while the VLM is being fine-tuned eventually, but for immediate response, it seems to me that there needs to be a sort of memory retrieval system that needs to come hand in hand with this. So I mean, you can treat this VLM as a system one, intuitive response, but there should be some simulation planning memory component that helps to augment this, so that you can adapt in real time, like without needing to fine-tune the whole model. So yeah, just opening this for discussion. Yeah.
I think I do agree with what you're trying to say, which is like there's a lot of this problem, not just in terms of what you're trying to say here, right? Whereas another way to look at this is like if you're talking about those action-based model like VLAs, you need to be able to do, your VLAs must be able to do inference at a speed that is comparable to the action, correct? So there's a control frequency versus an inference frequency. So if let's say you're inferring too slow as compared to your action, then you might already miss the position to grasp it by, or to miss to predict the next token. So I think that is like a problem that I think we should also look into, which is right now there's a really early stage in robotics that I think people are trying to get on board on this, but not heavily, been working onto this area. Whereas in language model training and like vision language model training, this kind of techniques has already been quite well used. I will agree. So in this case, right now, we are still lagging behind that. But I think right now we are focusing on, generating this data and seeing how well this vision language model can perform for specific robotics application. And then once that is done, the next step is to do what you are suggesting, right? Like in the sense whereby how can we do create adaptation, like let's say we're running some of these VLMs with the lower policy.
Don't worry, we are working hand in hand. I'm actually tackling the adaptation front right now, using some agentic model like TaskGen. Yeah, so when you finish your fine-tuning, you finish more experiments, I'm sure we can link the two systems together.
Sounds good.
Sounds good. Okay, next questions, please. Anyone else?
If you don't mind, I'd like to go next. For Jiafei, I am curious, are you familiar with the EMO3 models or the paper? Just for context, it's okay if you don't. But basically the premise of it was next token prediction. And what they did is they took a very typical branded down transformer model, and they did heavy tokenization into like a kind of discrete space for multimodality. So like perception, video generation. So it could do video generation, but also like perception, image perception, video perception. So I'm just curious about your thoughts on the potential for this kind of next token prediction, because it had on par performance with stuff like stable diffusion and other techniques that are used in transformer models. And I was wondering what your thoughts on that next token prediction, its powers and capabilities, and how it might be leveraged in your future research and your future ambitions.
Yeah, so I think maybe not the exact paper, but I think like this concept or this idea I sort of heard of it, and then I mean I'm not explaining this, but I think what I'm trying to think of is that for this kind of next token prediction, I think it's really it matters a lot more in terms of like for vision and language, whereas for robotics it's a bit different, right? Because like I guess what does the next token really mean in a robotics context? So in an action model, does it mean that the next token is like I guess like a delta, or does it mean like it's a robot join state, or is it like an effector position? So the representation of that next token, at least in the context of robotics, is not that clear. And also I think like it's harder because to influence the real world, or to like sort of affect the real world through manipulation, is much more difficult as compared to language-wise. Like language-wise, you sort of roughly have an idea that what the next token will most likely be based on the context of your current sentence or whatever, correct? But in robotics, if you are pushing a sphere, you can never really truly predict what is going to happen next, right? Because like the world is so custom. There's so much like ambiguity and chaos in the real world. So like action-wise, it's really hard for you to predict. So I guess like in that context, then maybe next token might not be that important as of now. I think finding the right kind of representation would be more important, and then to bootstrap the representation into like a low-level policy that can actually work. I think that matters more in robotics. Yeah.
Yeah, I'd say I agree with that, because in attention mechanisms and in transformer architectures, when you're processing language, the representation is already there, if that makes sense, because you already have the context of the language, and the different tokens, different words can all affect each other already. The language itself is already a representation space that is self-referential. Obviously, with proprioception and action models, what's the representation, or what are the different representations you need for that kind of like context processing? And I do think it's more important to explore the representations right now, while expanding the data sets and also building up the synthetic data sets, trying to find what representations work the most and work the best, and then building upon those representations into new potential architectures would be very exciting for the future, in my opinion.
Yeah, I do agree with you. I think another thing that I look into that's slightly different between robotics and vision is that if you have all these like foundation models that's out there, like GPT, Gemini, all these, they always evaluate on benchmarks, correct? So in their context, like maybe optimizing on that benchmark matters a lot more. But for robotics, that 1 or 2% difference might be negligible. Like you don't really tell what is the 1 or 2%, but you rather know that if something works versus something that don't work, that's the more obvious. So it's either it works or it don't work. So I think in that context, then maybe in this case, like we don't really put so much focus on that predicting the best next token, because like even if you predict the best next token, is that really considered like a good action? I think that's the hardest part to determine, right? Like for example, like if you ask a robot to pick up a ball and hand it to you, like how it picks up and how it hand it to you, whether it does it correctly, you can do it in very weird ways. But then as long as the ball ends on your hand, do you define that as a success or do you define that as a failure? So there's a lot of ambiguity in this context. And evaluation in robotics context is much more different as compared to like other domains. I think, and that's something that really requires a lot more work to think about, and that will definitely affect all the other model decisions that's going to be made. Yeah, hopefully that answers. I mean, I might be a bit detouring from the question, but yeah.
No, definitely. I love your thoughts, because you're obviously an expert in robotics. Robotics, I'm not really as in tune with. I spent a lot of time studying like neurosymbolic approaches and a lot of like language models and neural processing. So I always love to hear your thoughts.
Thanks. Yeah.
Yeah, thanks. Actually, this brought some insights to me. Like I was thinking about like how transformers for text, they learn the representation. Actually, it's because they have a huge corpus of text, and each subword or like each token could get some meaning based on like this next token prediction could give some meaning when you go into the embedding space. So what could be really lacking in robots is that there's not enough robots and not enough data. So right now, we might, if let's say we have 1 billion robots collecting data right now every second, I think there's still less data than the internet. So this is something that is a huge challenge in robotics. And so the question is, do we want to go the ChatGPT route of just getting a lot of data? Like, the sim to real, which is simulation to real life. The issue that is faced right now, the solution to that for robotics, guess what? Train on more data, train on more diverse scenarios, change the parameters. So it's like if a robot needs to walk on the ground, you change the ground surface, you change the wind, you change so you change the environment. But you see, let's say you have 10 environmental factors, each of them have 10 possibilities. It's exponential. How much training data can you actually generate to fit the real world scenario? So that's the question that I always like think about. And I think like, you can get all the synthetic data you need, but like what if something happens that is not preemptable? Like, so I think the robot needs to adapt on its own without this training data. And so the answer might lie outside of the training data, but more on the inference kind of like how they learn from real life and store some experience learning, and then from there you influence the behavior. I think that adaptiveness part, I think, is a key factor of why robotics cannot really work well right now. I mean, this is a bold claim.
Yeah, I think John, I sort of agree with you to some to a certain extent. I think also one of the ways that why I think robotics doesn't really work well as of now is that if you look at ChatGPT, if ChatGPT works, decently well to maybe like, I guess like 80%, times 80% of the time it gets what you want, correct? You can still deploy that model. But if today I have a robot that put in your house and I tell you that you only succeed 80%, will you want to let me put that robot in your house and do house chore for you? The answer might be no, because that 20% might end up in catastrophic failure, or it might destroy your house, for example. So in that context, we are not able to actually put this out there into end user as easy as deploying like ChatGPT. So I think because the cost of failure is much higher in this context. Yeah. So also because of that, you are not able to get enough feedback. I guess like different iteration of ChatGPT sort of improve also based on how humans are using this and consistently giving feedback. For all we are providing more data for OpenAI.
Yeah, that's a good point there. So like I think this point on like the data side, you just need more data, and like, but that's one part of the solution. The other part, as what I said, is the learning mechanisms beyond the data. I think this is lacking. So like right now, I think there's a general understanding that reasoning is important and so on. So I do see that this will, like what you have done for the failure reasoning and so on, this will help to increase the ability of the robot to adapt beyond the 80% to like 90 to 100% just by learning from like its experiences. And I think that part, once you hone in more on that, yeah, then the system can be more and more reliable. Actually, this robotics thing and AI agents right now have a lot of parallels. Like AI agents, they can potentially do a lot of things, but there's a significant failure rate, and that's actually impeding their use for business use cases right now. So I also think the missing ingredient for that is adaptation. Like you need to take in environment feedback and learn fast. And that learn fast is not fine-tuning. That learn fast needs to be another mechanism. Yeah, which is what I've been talking about the whole time. Yep.
Yeah. I think I do agree with you. So like the consequences of failure is really high, right? So I think like for this kind of system to be deployable in the real world, even for like if you look at autonomous driving, I think at the early stage of autonomous driving, there is still going to be someone behind the wheel remotely somewhere else, while someone else sits in this car that's autonomous in some context, correct? So in that sense, you're not fully autonomous, but you are ensuring that there's a fail mechanism or there's things in place to do quick adaptations or in case of something fail. So for example, if in the case of self-driving, if something is going to go wrong, a person that's remotely somewhere else will be able to take over the wheel, correct? Yeah, I think it's in the same context. But I think the difference is that, for autonomous driving, you are able to deploy that into the real world, even though there is a risk of doing that. Yeah. So I think like this kind of fail-safe mechanism need to be in place in order for us to actually deploy robotic system at scale into the real world, and same as the agent-based system, right? So, yeah.
Cool. Yeah. Anyway, next, anyone else has questions to ask? Yeah, we can go to the next question. Okay, if there's no one that has any questions, that's great, because I do have quite a lot of questions. So anytime if you want to ask anything, just type in the chat that I can refer to you. So for the last like 10 minutes or so, maybe we talk more about the future of robotics and like how we can achieve a system whereby, you know, we can learn from limited data. Synthetic data is, I think, the approach that Jiafei is focusing on to basically try to bridge the gap between real world data and learning by just giving more data. And by doing so, it helps the robot to learn examples of like how it fails, how to correct from its failures. And for the AHA paper that showed that it increased performance significantly, like it beat all other models, which is quite a good achievement, by the way. Yep. So the main thing that I have to think about right now is that, like, do you think, so this is the question I need to ask you, like, do you think we can model the entire world in a simulation right now? Do you think it's possible?
I think that's a good question, right? So I think like I think there's definitely I wouldn't say that you are able to model the entire world, you know, but I'm definitely believing that, you know, simulation is one of the more feasible way to sort of scale up data and to sort of you know, people always use this term like image net moment robotics. I think I was fortunate to have a chat with Feifei about this topic, and she was telling me that, you know, like when you really talk about image net moment robotics, you're talking about a way that is able to sustain and continuously generate data, and you know, maybe even towards an infinite process. So I think simulation definitely opens up that process to us. I would say that, you know, there's bound to be like last mile fine tuning on real world data, because you need to be able to have that personalization process. But I think learning majority part of the, you know, policy, or learning the majority part of the process, you know, within simulation will be actually achievable, you know, depending on how large the simulation is. And also I think like with a lot of this work recently that comes out that focus on, you know, generating 3D assets or procedurally generating 3D scenes, I think that actually give rise to a lot of potential in, you know, using simulation. And there's a lot of startups that actually focus on building simulation. So I think like maybe, I don't think you can simulate the whole world, but I think you can simulate things that's interesting, that's useful, or that's the right representation that could be used for, you know, training things that will work in the real world. Yeah.
Yeah, that's very nice. Like I also think simulation can help a lot, because with simulation you don't have to get the real world experiences. You don't have to like crash your car 1 million times to learn how to park if you could simulate it. Yeah. Then actually that's the thing that, like, you know, in evolution, right? Like as the brain evolves, like from nematode all the way until our human brains right now, if you read, like, there's one book that I read recently, it's called A Brief History of Intelligence by Max Bennett. And basically there's one part of that book that talks about like humans learn the way of mentally simulating things and like experiencing things in their brains. And then from that mental simulation, you know, you can choose better actions as compared to just reflex. Like, you know, sometimes if let's say, this reminds me of this method, you know, called the Monte Carlo method, where, you know, when people used to play blackjack, you know, like how do you know whether you should hit get the next card, or to stick, or like not get a card? And it turns out that there's a very simple strategy. You just simulate the next 1,000 draws, like randomly, and then you see how many percentage of it you win. Then you know whether or not like you should take or not. So as there's some value to simulation, in the sense that, like, if you're not sure whether to take action A or B, you take action A in your brain, and then you simulate what's the outcome, and versus action B, and then you simulate what's the outcome. Of course, there could be many possible outcomes, but you could like average it, or you just take the best outcome or something. That's the same method that is used in AlphaGo, AlphaZero. They use Monte Carlo tree search to do simulation. So simulation to me is very important. So if you can have an accurate world model simulation, it can be used to predict which action is good. Okay, but I don't think it's possible to generate synthetic data that can cover all ground. So the simulation part could potentially help to cover the ground in real time. So what do I mean by that is that, let's say if I've never been in this situation before, but my world model in the head is completely accurate, I can simulate either action A or action B in that particular context. So I narrow down the data to that context, and I run the simulation in my head. So I think something like that might benefit robotic policies, in the sense that you can do real-time simulation. You can treat it as system 2 thinking. Like you just run through the possibilities, and Yeah, I mean, I just want to run through this thought with you. Like, what do you think of it?
I agree with you. I think like simulation has been used in many different domains beyond just robotics, right? I think the thing about having this simulation is that you're able to have that controllable factor, which you don't have in the real world. But obviously, the simulator is as good as how well you can model the real world. So as you mentioned, right, you can model with a world model approach, or like other ways that you potentially could model for this simulation. I think the more accurate you are able to represent the real world, I think the more useful that simulator is in terms of generating useful representation for learning that could potentially be used like zero shot to the real world. So I think that's like something that I also have been thinking of a lot. I think even like maybe one thing that we also try to look into is like, especially nowadays with all these like VLMs, which are general purpose, a lot of these VLMs are already training on simulation data. So like, for example, like, if you give a ChatGPT like, a simulation image, and prompt it, you'll be able to, give you the same kind of reasoning. So like that sim to real domain gap doesn't really exist that much in this kind of VLMs. And in fact, people are using, game engine to generate data for training, generative models. So I think that's how simulation can really be used for, right, in that context.
Yeah. One radical thought here. Suppose you have a game engine in your head. Can you map the real world back to that game engine state to run simulation? So let's say right now the robot is in real world, like a vacuum robot, it sees an unknown object. Then based on all the sensors, it maps back and tries to reconstruct the world in the game in the head, like using Unity or something. You do that perception and you build that. And then from there, you can do like planning based on that simulation. Do you think it's possible? That means you reconstruct what you see in real world back in the game state.
I think that's an idea that is in robotics for quite some time, right? So people have been using like task and motion planning, whereby they do some kind of state estimation to estimate the state of the world. Obviously, if you're in simulation, you get a perfect state, and then you run some kind of motion planner to sort of like search through for potential solutions to solve the task before executing the solved solutions. So I think that's something that has been done. But the hard part about this is how do you have good estimation or state estimation of what happened in the real world. So that's one aspect. I guess like if you are talking about try to do this kind of estimation and modeling in your brain, I guess humans can do that, but a lot of times you're not able to be able to accurately infer the right kind of parameters to model some or to simulate some of these things. Although there is like a lot of work from like George Taliban that talks about intuitive physics and having this kind of physics engine in your mind that can sort of simulate what is going on in the real world. But I think that precision matters a lot. So if let's say a ball is like, I'm going to try to catch the ball in my hand, I can simulate in my mind that, okay, it's going to roughly hit, I'm going to catch it. But how precise and how timely this simulation is matters a lot in terms of execution, right? So if I simulate that it's going to hit, but then if I reach out my hand slightly later versus I reach out my hand earlier, you might just miss that ball. So I think in that context, I think maybe incorporating simulation and having a real world feedback loop that would be more useful. Yeah.
Cool. All right. So I think we have come to the end of today. There's a lot more that I'd like to discuss. So maybe we could ask you for another round, another time. And just want to pass the time on to you. Do you have any last concluding notes you want to share with everyone?
No, I think hopefully everyone likes the talk and enjoys the three words that we have. Like if anyone has any more questions, feel free to reach out to me. Or interested in these topics, feel free to reach out and we can discuss more offline.
Yeah, looking forward to more great works from you and your lab, and I'm sure you'll come up with something to crack this robotics problem. I have faith in you. So
yeah, thanks, Sean.
All the best, and thanks everyone for staying. Yeah, see you everyone.
Bye.